Stokes theorem, the last of the three classic theorems in analysis. The first, Green's theorem; the second, the divergence or Gauss's theorem; then thirdly, Stokes theorem. All three relate to the same idea of computing a line integral, whether using a single integral, a double integral, or a triple integral. Here, Stokes' theorem is concerned with evaluating, if you look at the theorem, evaluating the line integral using a double integral. He does this by taking what Green's theorem had initiated with looking at some curve about a region, and then moving that curve here along the so-called line in a certain direction or orientation. So the energy is left inside of the mass, and so we're investigating the energy within this surface with a boundary that is well defined. It is possible then to look at the amount of energy exerted along this surface with respect to the line integral by looking at how much in terms of the rotation of this curl, the rotation of the energy from the vector field, how much of that energy that is exhibited from the particular solid with you see here they have the unit normal vector pointing up with an outward unit normal vector. And so, in other words, whether you look along the curve to measure the energy, or if you look at the entire surface to measure the amount of curl, what Stokes is saying is that you come up with the same thing if provided that certain preliminary conditions are true. And that is that here S must be an oriented surface. That is that if you're going to be examining the outer rim of the surface, you must stay there and continue to focus on the outer rim of that surface. So here with a unit normal vector that's directed outward, bounded by a piecewise smooth, simple closed curve, the curve cannot cross itself. If it does, then you even violate the orientation, the orientable nature of the surface. With positive orientation, that is, as you move along the curve, the region is lies to the to the left of the curve. If F is a vector field whose component functions, that is M, N, and P, have continuous first partial derivatives on an open region, why is that necessary? Well, that's necessary for the curl, but it's also necessary and important for Green's theorem. So the first partial derivatives are continuous on two spaces, on the region containing S and then also C. Well, obviously C is connected to S. C is just a curve about the so-called surface. So you want to examine either one, examine the curve, that's the boundary for the surface, or you can investigate the surface itself. If you investigate the surface itself, then we're using Stokes' theorem. If you investigate the energy along the curve, then you're using Green's theorem. So I think with that, let's look at some problems. Again, this single integral is the line integral over the curve exhibited by the vector field, and then that can be computed using a double integral with respect to the curl. So if we take this problem here, well, we need a few things. We need the curl, so let's get that. So the curl, you recall, is found in this fashion. So the first row would be the components I, J, and K. The second row is the partial derivative operators, and then the third row would be the vector components M, N, and P. So this is negative Y plus Z, X minus Z, then X minus Y. So we delete the ith row and column. We have the subdeterminant, so it's the crisscross, the partial of this term with respect to Y. That's negative 1, minus the partial of this term with respect to Z. That becomes a negative 1, so it's minus here a negative 1. Then we go to the jth position, delete its row and column. So we operate the partial of this term with respect to X, that's 1. Then minus the partial of this term with respect to Z, that's 1. Then we go to the kth position, delete its row and column. So we have the determinant of the submatrix is this partial with respect to X, which is 1. Then minus this partial with respect to Y, that's a negative 1. So we clean this up. This is 0, and this is 0. So all we have left here is 2K. And we look at capital G, which is Z minus G of XY. So this is Z minus 9 plus X squared plus Y squared. And so the gradient of G is 2xi plus 2yj plus k. Why do we need the gradient? Well, here's my conjecture. The line integral of f dot dr, this is Stokes theorem, is the double integral over the surface of here, the dot product of the curl of f dot within ds. I can simplify that, and what I have is the double integral over the region. Why do we go there? Because this gets us back actually to Green's theorem. It's the curl of f, the dot product of that with the gradient of g dA. This is my contribution to one aspect of the mathematics. So if that be the case, then we have this double integral. Oh, what is the region? Here, the region. That's in the xy plane, right? Here, if z is equal to 0, if you deal with the xy plane, then you have x squared plus y squared is equal to 9. So that is the region. It's simply r is bounded from 0 to 3, and theta, it's a complete circle, is bounded from 0 to 2 pi. So we have this curl of f dot with the gradient of g dA So this is the double integral. The curl came out to be 2k. That's dot product with the gradient, which is 2xi plus 2yj plus k over the region here with respect to the change in the area. Do that dot product, all you have is just 2. So we're going to go ahead and convert to cylindrical coordinates. R goes from 0 to 3. Theta goes from 0 to 2 pi. So integrate with respect to R. So that gives us this integral from 0 to 2 pi. Here we get 2r squared divided by 2. So it's just r squared evaluated from 0 to 3 d theta. That gives us 9 times the integral from 0 to 2 pi. You know, that's just 9 times 2 pi. This is 9 theta evaluated from 0 to 2 pi. You get 18 pi. So I will use our contribution to Stokes theorem. What is our contribution? The equivalence here in terms of using the gradient. Let's look at another problem. Again, we need the curl, and then we need the gradient. So let's get the curl first. So the curl ijk, the partial with respect to x, partial with respect to y, and the partial with respect to z. Then we need m, n, and p. So delete the ith row and column. So that gives us the partial here with respect to y. That's 2y minus the partial of this term with respect to z, 0. Go to the jth position, delete the jth row and column. That's the partial of here with respect to x. That's 0. Then minus the partial of this term with respect to z. That's minus 2z. Go to the kth position, delete the kth row and column. So is this partial with respect to x? That's 2 minus this partial with respect to y. That's 0. So here we have for the curl 2yi plus 2zj plus 2k. The gradient, well, first we need g. G is this z and then everything to the same side as z. So it's z plus x squared plus y squared minus 1. So the gradient of g, you can do better than that, Ernest. So the gradient of g is 2xi plus 2yj plus k. I think in my mind I'm writing better than how it's coming out. But anyway, that's a theological point. Well, so you see the region is going to be the circle with radius 1, and it's a complete circle, right? let z equal to 0, then all you have is x squared plus y squared is equal to 1. So we have this double integral. This is first over this surface in the space. So the curl came out to be 2yi plus 2zj plus 2k. Dot product with the gradient 2xi plus 2yj plus k. This is dA. To simplify this, we have 4xy plus 4yz, and then plus 2. Now that z is equal to 1 minus x squared minus y squared. And so we convert here to the region by writing everything in terms of x and y. This is 4xy plus 4y times 1 minus x squared minus y squared. And then this is plus 2 here, dA. Simplify that again. This is 4xy plus 4y minus 4. Let's leave that so I can show you something. So this is 4y times 1, and then let's say minus here 4y times x squared plus y squared. That's plus 2 dA. Now I'm going to convert to cylindrical coordinates. And so this 4xy is 4r cosine times r sine. So this is 4r squared cosine theta sine theta plus 4r sine theta minus 4r sine theta. X squared plus y squared is r squared. This is plus 2. This is r. I'm going to do d theta dr. Theta goes from 0 to 1, and r goes, well, theta goes from 0 to 2 pi. And then r goes from 0 to 1. So this is the integral from 0 to 1, the integral from 0 to 2 pi. Let's run this r through there. So this is 4 r to the third cosine theta sine theta plus 4r squared sine theta minus 4r squared, well, 4r cubed times r is 4r to the fourth. Do you see that? This is r squared times r, so that's r to the fourth. This is sine theta plus 2r d theta dr. Now why am I picking on theta first? Because I'm getting a complete path from 0 to 2 pi, right? It's a closed region. Closed regions tend to tell us that the energy exerted here would would all equalize and just come out to be 0. So I'm predicting this is going to be 0, this is going to be 0, that's going to be 0. Let's go ahead and get that out the way if that is the case. All right. Ooh, I need more space. Okay, so if that's the case, we're going to integrate with respect to theta. So here we can integrate directly on this sine theta, right? Those sine thetas there, and it could have been easier to just factor out that sine theta and just wrote it by itself times those terms, but it's okay. Here we use a u du substitution. Let u equal to sine theta, du is cosine theta. So when we do that, this is 4r to the third, and if u is sine, du is cosine theta d theta, then we integrate that u, we get u squared divided by 2. So I'm just going to write it, that's sine squared theta divided by 2. Okay, then we integrate the sine here, we get minus 4r squared cosine theta. And this is the integration of this sine is negative cosine, negative times that negative is positive, 4r to the fourth cosine theta plus 2r theta. Theta is evaluated from 0 to 2 pi. And now here we have dr. So look, sine of 2 pi is 0, minus sine of 0 is 0. Cosine of 2 pi is 1, then it's minus cosine of 0, which is 1. So you get 1 minus 1, that's 0. You get here again 1 minus 1, that's 0. So do you see where this is 0, that term is 0, this term is 0. So what we have left is the integral from 0 to 1 of this 2 pi, what is 2r times theta. Theta is 2 pi. So that's 4 pi r. 4 pi r dr. Integrate with respect to r. We get 4 pi r squared all over 2. It's evaluated from 0 to 1. That just gives us, here we get 2, r is 1, so it just gives us 2 pi. And see if I can grab this and put this on the next page. Okay. So we need the curl. Partial with respect to x, partial with respect to y, partial with respect to z. Here this is z squared, y, and then z. So we do our partial. Here we cancel out the ith row and column. So we do the partial with respect to y, that's 0 on this guy. Then the partial of this term with respect to z, that's 0. Delete the jth row and column. Partial of this term with respect to x, that's 0, minus the partial of this term with respect to z, that's minus 2z. Then we delete here for k, delete the kth row and column. This partial with respect to y, that's 0, minus the partial of this term with, well, this partial with respect to x, well, that's 0. Then this partial with respect to y, and that's 0. So all we have left here is 2zj. Now g is z minus the square root of 4 minus x squared minus y squared. Well, we need those partial derivatives to get the gradient. So the gradient of g here for the ith position, this is negative, then it's 1/2. Take the derivative of this radical, 4 minus x squared minus y squared is to the negative 1/2. Times the partial of the inside with respect to x. It's negative 2x. So do you see that this is going to be just x divided by the square root? The same term here for y or for j. So this becomes y over. Simplify this, same scenario, symmetry there. So this is over the square root of 4 minus x squared minus y squared. This is j, and then the partial here with respect to z, that's just 1 times k. We clean that up. This is the gradient of g is x over the square root of 4 minus x squared minus y squared I plus y all over the square root of 4 minus x squared minus y squared j, and then plus k. So this double integral over the solid, this is the curl dot product with the gradient. So the curl, all we had there was 2zj, and then the gradient is x over the square root of 4 minus x squared minus y squared I plus y over the square root of 4 minus x squared minus y squared j, and then plus k. And this is with respect to dA. Good. So in the dot product, all you have that's contributing here will be the jth components. So this is the double integral over the solid of 2zy all over the square root of 4 minus x squared minus y squared dA. Now z is equal to that radical. It's the double integral here now over the region. I'm going to get rid of z. This is 2 y times z, which is the square root of 4 minus x squared minus y squared all over the square root of 4 minus x squared minus y squared. Now the radicals cancel. So we have this double integral over the region of 2y dA. Well, what is the region? Well, here again, let z equal to 0. This implies that you have 0 is equal to 4 minus x squared minus y squared. So that is x squared plus y squared is equal to 4. So you see that the region is r goes from 0 to 2, then theta goes from 0 to 2 pi. So this is the double integral of 2r sine theta, and then times r d theta dr. Theta goes from 0 to 2 pi. R goes from 0 to 2. Again, integrating on that sign, you're going to get cosine on the closed interval here. It's going to give you 0 for the answer. Now, if you see that, you can just go ahead and just say 0 without even having to do all this preliminary information. So this is 2r squared sine theta d theta dr. So integrate with respect to that sign. So it gives us -2, the integral from 0 to 2. And this is r squared cosine theta. That's evaluated from 0 to 2 pi. And here we have dr. So cosine of 2 pi is 1. Then minus cosine of 0 is 1. So 1 minus 1 is 0. Right? That's it, folks. Thank you. God bless you.